Hello there, welcome aboard lads. Today we're still talking about the heat equation. We now present to all of you some remarks. So the first remark says that the theorem 10.1 seen in episode 1 show that the heat equation has a strong regularizing effect on the initial data u0. We note that the solution uxt is infinity in x for each t positive. Even if u0 is not continuous, as we saw with u0 in L2 of omega, or in HK and verifying 8, it results from this that the heat equation is irreversible. Usually, we cannot solve the following problem with the equation 9, 10, and 11, which are the directly boundary condition for the heat equation, but with final data. It will necessarily implies the three equations will necessarily imply that ut is in infinity omega bar with the jth Laplacian of ut equals 0 on gamma for all j positive. Ut is in infinity of omega bar comes from what we just said on the strong regularizing effect. U is in infinity omega bar times 0 infinity, so it works for big T. Then, as you supposedly verify 9, 10, and 11, we have that U equals the derivative of U with respect to time, and so on, up to the jth derivative of U with respect to time, and so on, equals 0 for j on gamma times 0t. Because we know from 10 that U is equal to 0 on gamma times 0t, and we derive with respect to t for all j positive. Due to continuity, we have the triangle equation, the jth derivative of ut with respect to time equals 0 for all j on gamma. Besides, we got that the derivative of u with respect to time is equal to the Laplacian of u on gamma on omega times 0t, and we do the same thing, replacing the derivative of u with respect to time by Laplacian of u, which gives us these equations. By continuity, it yields the square equation. So the jth derivative of ut with respect to time is equal to the jth Laplacian of ut for all g on omega bar. Comparing triangle and square, we obtain that the jth Laplacian of ut is equal to 0 for all j on gamma. So we have u of ut is in infinity omega bar, and the jth Laplacian of ut equals 0 for all j on gamma. But these two conditions are not sufficient to guarantee the existence of a solution for the problem 9, 10, and 11. We must not confuse the problem 9, 10, 11 with the problem 9 prime, 10, 11, where 9 prime is the following equation: minus derivative of u with respect to time minus Laplacian of u equals 0 omega times 0t, which always has a unique solution for each ut in L2 omega. Indeed, we just have to change t in big T minus t, giving us 9 prime, 10, and 11, where if we just consider big T minus t as t tilde, we just have then to apply the theorem 10.1 we saw before in episode 1, and we have the same case. In the remark 2, the results we have seen so far are true with slight changes for the Cauchy problem with the Neumann condition. Finally, in the remark 3, When omega is bounded, the problem 1, 2, 3 can be solved by decomposing onto a Hilbert basis of L2 of omega. It is very convenient to choose a basis ei of x for I greater or equal to 1 for L2 of omega consisting of eigenfunctions of the Laplacian with directly boundary conditions. That is to say, minus Laplacian of ei equals lambda I ei on omega and ei equals 0 on gamma. We are looking for a solution of 1, 2, 3 in the form of 12, where uxt is equal to the sum from I equals 1 to infinity of ait ei of x, which is called the Fourier method or the separation of variables. We immediately see that we necessarily have ai prime of t plus lambda I ai of t equals 0. Thus, ai of t equals ai 0 exponential of minus lambda I times t. Because we just have to solve the blue-framed differential equations in order to get the expression of ai of t. The constants ai0 are determined from the relation u0 of x equals the sum of I equals 1 for I equals 1 to infinity of ai0 ei of x, which is just the expression 12 with t equals 0. That is to say, the solution of 1, 2, 3 is given by 14 uxt equals the sum from I equals 1 to infinity of ai0 exponential of minus lambda I t ei of x, where the constants ai0 are the components of u0 of x in the basis ei. So that's the end of the video. Please leave a like and subscribe, and don't forget to pursue your journey in the math world. Thank you.